Hello, everybody. So let's get started today. Let me share my screen. We'll continue to part 2 of sheet metal working. So we divided the sheet metal working to cutting and forming. And you saw the different categories of basically sheet metal working. All right. So as a quick recap, as we talk about cutting, in particular, we calculated how much force do we need to cut a certain, let's say, length or width and thickness of a material. So the way that we calculated, we said, well, this force results in shearing stress in basically this plate. And we said cutting happens when the shearing stress, or let's say cutting happens if the maximum shearing stress in the plate reach to its ultimate shearing strength, which is SUS, all right? We show SUS to indicate the ultimate shearing strength, ultimate shearing strength. And we also said that we can use different criteria. For example, we used Tresca, if you recall, and we or let's just call it the Tresca criterion. And I need to work on my handwriting. And we said this SUS is equal to half of SUT, which is basically the ultimate tensile strength. All right, so this is then SUT, ultimate tensile strength. This is the value that we have on table, and that's the value we can measure by doing the tensile test. So the tau max, we calculated that this tau max for like a plate that has a cross section, like a rectangular cross section, let's call it A, is something like 3 divided by 2 F divided by A, all right, which A is B multiplied by H here, obviously. So from here, we could calculate force that requires to cut this plate, which it gives us 1/3 basically area multiplied by SUT. So that's one formula that we got, and we said that's an important formula. Also, if we need to know how much power we need, when we talk about power, of course, we are talking about the speed or the velocity, right? The velocity. So the power then is going to be force multiplied by how fast we want it to be cut, the velocity or the linear velocity. So this is the conclusion that we made last time. Today we're going to talk about the engineering analysis for bending, basically. That's the plan. But before we get to bending, we know that bending happens, last time we talked about it, when the material gets to its plastic deformation. Unless if you are in elastic deformation, after we bend something, it's going to return back to its original shape, right? We need to get it to the plastic deformation. That's obvious because we want permanent deformation, right? But now the question is how small this radius can be. Can it be 0? So let's say that I have a plate. Let's say this is the plate. And let's say I want to bend it over maybe a fixed cylinder. Better now, all right? So of course I apply a bending load or a pure bending M to bend it. So this radius, how small it can be before we tear down the material. So the question that we want to answer is, what is the minimum radius that we can get? Let's go back and check the formula that we learned in MEC 2 or MEC 360. Let's see if we can remember those, all right? So if you recall, we remember that for bending, let's say if the cross section of this area or this whatever beam or whatever it is, let me move this one a little bit over there. So let's say this is our cross section. So that's the cross section basically. Right? So when we bend something, let's assume that this is a beam for simplicity. When we bend something, we learn that there is something that we call a neutral axis, which passes through the centroid of the cross section. I hope you guys remember that. And we learn a formula. Under bending, the stress is going to be MC divided by I, which basically C is the, we can say is the distance between the neutral axis. Let me show it here. So that's basically C, the distance, because we are calculating the maximum stress. So the maximum stress happens either at the top layer, which is under tension, and the bottom layer when it is under compression. All right, and C is the distance between the top layer to the neutral axis or the bottom layer because here we have a rectangular cross section, they are the same basically. All right, so sigma max here, MC divided by I, which if the blade that, sorry, not the blade, the plate that I have or the beam that I have, let's say if this, the thickness is T, let's show it by T, then obviously this C is equal to half of the thickness, right? So that's one thing that we learned. And also, if you recall, we learned that if I apply a bending load to a beam, it's going to become a curve shape. It's not straight. And 1 over R, we call it curvature, which this R is the radius of the curvature. And 1 over R, we call it curvature. And if you recall, we learn a formula, 1 over R is M over EI. Right? These are a standard formula for a beam under bending, all right? We haven't invented them. They are a standard formula, which you learn. The proofs are in one of those classic books in MEC 2 or MEC 360, whatever books you have studied before, right? So if I compare these two formula, what do I get? I will get R equal to EC divided by sigma. All right, and I can replace C with the thickness, so R will be ET divided by 2 sigma. That's the formula I get for R. And now, what is the minimum R? Of course, the minimum R is before breaking, right? So the maximum, so I write down over here, the maximum stress before failure. So the maximum stress before failure is when we get to the ultimate tensile strength, right? SUT. If I replace that one with that formula over there, we can conclude that if the maximum stress is SUT, then the minimum radius is ET over 2 SUT. And again, this is another important formula that we need to consider when we design something for bending. So it depends on the thickness of the sheet metal that we are bending, depends on its material, here module of elasticity and SUT, and there is a limitation how much it can be bent, basically, without failing. Otherwise, let's say in this example, it's if I bend it maybe over this big cylinder, like this one, maybe nothing will happen, everything is okay. But if I continue bending it to this smaller one, maybe a crack happens at the top and the whole plate breaks, basically. All right, so that's the idea. There is then, depends on the material, there is a minimum radius that we can bend something. And again, it is important when we design a die or a mold, but we call it die for bending. Basically, that how much is the radius that we can bend something without breaking it. All right. So far, guys, is there any question? So that's then the second important formula that we need to basically know how to use it. All right. So silent, I consider that you are okay, and you know where this formula basically came from, right? And again, this is all returned back to the basic concept and basic formula that we learned before. Okay, so in that sense, if there is no question, let's move on. Now, the second topic that we have in hand is, now that we know how much we are allowed to bend a plate or a sheet metal, now we need to know how much force we need to get to that basically radius that we want, all right? So if you recall last session, we said that there are two types of bending. One, we call it V bending because of the shape, and another one, we call it edge bending. Again, the shapes implied, all right? Each of them has a geometry, as you can see, and for the amount of force that we need, based on the engineering books, again, the proof, maybe if it's not in your textbook, you can Google it. Maybe there is another textbook which provide the proof for this, but it again return back to some empirical data and also some basic concept in bending. So for V bending, V has this formula, 4W squared 3D SUT. And for the edge bending, F has this formula. I'll explain the parameters in a moment. WT squared 3D SUT. So in this formula, obviously, SUT is the material strength, the ultimate strength of the material. T is the thickness, like the on the diagram on the left, you see it shows, and same for this one over here. T is the thickness of the basically the sheet. And W is the width, like depth of these things that you see. So W then is the width of the sheet, all right? That's about W. And D, the definition for D is the opening of the die. Opening of the die. So basically you can get to the same alpha using different D, all right? Then the amount of force is gonna change. And the definition for D over here, as you can see on this schematic, sort of you can guess that this is where the bending starts, right? And based on geometry, we can calculate D. And always remember, when we talk about the radius of bending, we are talking about the radius of the neutral basically, let's say, plane, all right? So previous example, or here when we talk about radius, the radius is the radius of the neutral axis, basically. Not a good color. All right, so here is the radius then. It's not the inner radius, it's not the outer radius, it's the basically the radius of the neutral axis. All right, so somebody has a question?
Yeah, I had a question. I don't know if it was answered in the chat or answered yet, but I saw it in the chat. I thought it was a good question. Is this the minimum force that's required to bend these sheets?
That's a good question. Thanks, Joshua. So this is the force that's required for us to get the material to its plastic deformation, to get a permanent, basically, deformation that we want. If we pass this force, what will happen? The material is going to pass the SUT and it's going to fail. It's going to crack. So sort of we can say that's the maximum force that we are allowed to apply. So then you may say, what if I apply less force? If you apply less force, then you don't get to the geometry that you want, which is the next topic that I'm going to talk about. All right? So, but again, that's a good point. This is, if we exceed this force, then our stress is going to exceed SUT and the things is going to crack and fails. We don't want that. If we apply less force, then what's going to happen? We are not going to get to the bending that we want. So then to answer your question, on paper, this is the just amount of force that we need to get to the geometry that we want. Does that answer your question, Joshua?
Yeah, so it's sort of a balancing act between getting the correct dimensions and breaking the sheet.
Exactly.
Okay, thanks.
Great. So let's solve one quick example together. So we want to bend, let's say, a sheet that the thickness, it's 3 millimeters. You see it on this diagram. All right. And also the width or the depth of this sheet going to your screen is 45 millimeters. The die that we use has an opening of 25 millimeters. All right. So in this question, instead of alpha, we have D. In some question, you may have the alpha, the angle of that V. So then you could calculate the opening of the die. And we want to calculate the amount of force that we need. Of course, it's a V die, and we know which formula we need to use, right? So I write down over here, F, then the force that I need is going to be 4W T² 3D S ultimate tensile. I replace those for the widths. We set 45, thickness 3, and the opening is 25. So SUT, it depends on the material. Let's say in this example, if this sheet is made out of a steel, then we go to our table and look up the SUT for a steel, probably for the type of steel that we wanted to use here. The number is maybe 850 megapascal or around that. If it is aluminum, then SUT is a smaller, 465, one type of aluminum. I just want to give you an idea. So as you can see, the higher the SUT, and it was obvious, more force you need to bend it, all right? So very simple example to give you an idea, the range of force that you need to bend like a plate, relatively small thickness, 3 millimeters, to like an opening 120 degree here or opening die 25 millimeters. Okay, so very simple. So do you guys have any questions so far for this example? I guess it's very simple and very straightforward, right? So let's then make it more interesting. Well, So when we apply load, again, you learn it in one of the mechanics of material courses, either Mech 2 or Mech 3. When you apply load, let's say a simple scenario, just a rod, you apply a tension and you release the tension, the load, return back to its original shape as long as you stay in elastic region, all right? So this is something that we learn. And we learned that there is like a graph, stress-strain diagram, right? Let me draw the, let's say this is maybe a bar. And let's say the cross-section is just a simple cross-section, like it's just a rod. And let's say in this case, we apply a tension. All right, so we apply a tension, maybe F, to this rod. A classic graph that we know we get, which we call it a stress-strain graph, is going to look like something like this. Let's say this is the sigma stress, and the x-axis is epsilon strain. All right, and we know that this graph is in most of for most of materials will get to a shape which is like a linear shape, more like, let's say this one, and then after that it's like, let's show a simple case. It's more like a curve, all right? And we know up to this linear point, we call it the elastic region, which we said this elastic region corresponds to, let's say this point, we call it epsilon y, and the stress we get to Sy, the yielding strength of the material, all right? So if we release the load from here, obviously we return back to point 0. And this is the elastic deformation. But if we want permanent deformation, we need to pass that point, and we need to get to the ultimate tensile strength of the material, which, again, for simplicity, let's assume that this is this point at the very, very top. A little bit over there. All right, so then this point is our SUT. And over here, let's for now call it epsilon of the load that we applied. We applied the load, we don't know how much it is, but it is a load that gets us to the ultimate tensile strength in the material, which there is a point that we want deformation, a permanent deformation. If I release the basically load, do I get this epsilon load that I wanted? So that's my question. So previous one, when we get to epsilon y, if I release the load, the things is going to return back to 0. So I don't get any permanent deformation. At this epsilon load, if I release the load, what will happen? Does the material return back to its original shape? And does it stay at where I am? Do you know the answer? Josh, do you have any idea? So that's the question. I'm asking, if I release the load now here, do I get epsilon load, like the material stay at that point, or return back to 0?
Can I say?
Yeah, go ahead, Ahmad.
Oh yeah, so it was just like, I think it'll not return back to 0, and it'll not even stay there. I think there'll be a little bit of spring back. And it'll make a new elastic module for itself, where it'll be linear in that region, I guess.
Okay, so do you remember from any of the past courses that how approximately we can say where it goes?
Can I say?
Yeah, go ahead, Panos.
It will spring back the same distance that's up to epsilon y.
So, okay, Panos is suggesting it goes back to epsilon y.
No, the same distance from 0 to epsilon y.
All right. So can we say then it's gonna it's gonna get from that point. If I draw a parallel line, it's gonna come back to a point where it is. Panos, can we say it's gonna get there?
Yes.
All right. So then that's what we learned before, right? We said if we draw a parallel line, depends on the E modulo of elasticity, the slope of these things. If you remember the slope of these things, alpha gives us the modulo of elasticity. We will get to this epsilon, which for now, let's call it F final. This is where we are going to get, all right? And you guys, you were right. So it's going to then spring back. And how much is going to spring back? This is the amount that is going to spring back. All right, this is something that we saw in the past and we learned it before. And epsilon final is the permanent deformation that we get, right? So this is then the permanent deformation.
Is the spring back equal to EY? Epsilon y, I mean.
No, it's not. Because it depends on SUT, depends on other parameters here. So it can be anything, right? For example, if E is very big, this number is going to be very small. So they are not equal. All right?
Wouldn't it be epsilon load minus epsilon y?
It's going to be epsilon load. So we can write down like something like this. A spring back, let's call it delta epsilon. So delta epsilon is going to be epsilon load minus epsilon final. Not epsilon y, right? Okay, is it clear, Panos?
Yeah, it's clear. Thank you.
All right, good. So now let's make it something relevant to what we want to discuss, which is bending, right? Let's say we have, maybe for simplicity, a beam. And this beam, this time, instead of tension, it is under bending M. All right? So, and let's say the cross section of this beam is, maybe for simplicity, just a rectangular shape, right? So again, just to refresh your memory of the formula that we learned in the past, we said under bending, the stress sigma is M CI, and the curvature 1 over R is M over EI, all right? So for simplicity, let's show this 1 over R by K. And we call it curvature. It's customary that people, they show it by K, okay? Now let's draw the same diagram for bending. So something like, maybe I need more room. Okay. So let's say that this time this is going to be M, bending the load, and this one is going to be K, which K is 1 over R. All right, this is the graph that we want to get. If we do a test for this material, similar to the tensile test, but this time for bending, the graph that we are going to get is going to be very similar to the tensile test, basically. So it's going to be like a straight line, and then after that, it's going to be like a, oops, not that one. It's going to be like a curve like that. Right? We're getting something like that. So The same idea, the same things, because that's the same concept basically. When something is under bending, it's sort of under tensile stresses basically, but it's not, it's a normal stress, but the different comes from a different load. So on this graph, like this point, let's for now call it KY, all right? Like curvature of elastic. And the load that I need to get to that point is going to be My. Can we calculate this Ky or My? Yeah, let's try. So this is the only tools that we have, right? We have like this formula 1 and we have this formula 2. Let's see if we can use these two formula to calculate Ky, all right? So I know that at this My, the stress gets to Sy. So if I use formula 1, we know that Sy is going to be My C divided by I, all right? And from formula 2, I know that Ky is going to be equal to My divided by Ei. If I simplify these two formula, what do I get? Ky, I can simplify this one, so it's going to be Sy divided by Ec, all right? So this is then the curvature of elastic. And again, don't forget the, like C is the thickness. Let me show it here. Like the thickness between neutral axis and from the top or bottom, all right? So this is what we call it C. Let's say if the thickness of the things that we have is T, then simply this C is equal to half of T, all right? E is module of elasticity and Sy, we know, is the yielding strength. That's Ky. So let's say that we want permanent deformation. If I want permanent deformation, then I need to apply my load to get to that, this basically SUT. So this is where I need to get, so let's call it K load. And at this point, it's going to be M load, the load that I applied, right? And now let's assume that we like to get to these like K load. That's our intention. This is the amount of radius that we want, or bending that we want permanently to stay in these things. But it's not going to stay there. Why? Because we just learned that it's going to spring back. How much is going to spring back? So if I draw a parallel line, it's going to come back over here. So in other words, this is going to be my K final, basically, all right? And this amount that we saw here is going to be the spring back. Let's call it delta K for now. So our K final, let's continue on the next page. Oh no, that's a different things. So I'll write it down over here. Our K final is going to be equal to K load minus delta K, all right? So again, don't forget this K load is what we wanted. This is the, let's say, curvature of the die. This is what we designed. We wanted it to get to that curvature. But instead what we get is going to be a different number. It's going to be a smaller number, smaller curvature, bigger radius, because it's going to open up. The radius becomes larger, right? So, but now we need to answer this question. How much is this delta K? Can we calculate it? That's the question that we like to answer. So let's get here and we summarize things that we just learned. Let's say that we design a simple die to bend this simple plate or sheet to this curvature that we want. Again, I emphasize when we say radius or curvature, we mean the curvature of the, like this neutral plane, right? So the one that passed through the centroid of the cross section. This one is not the cross section, right? Cross section is the cross section of this sheet metal plate. All right. So the radius of this one, let's say this is the radius. This is the R load. All right, this is the radius of what we wanted. We apply load because we wanted to get to this radius, and K load is the curvature is 1 over R load. One over R load. So we know this number, this is what we wanted. But we know the moment that we release this load, we are gonna get to the K final, which is basically K load minus delta K. So delta K again has a formula. It's a relatively large formula, delta K. And I'm not gonna prove it here, but this is something, again, important. You need to know this one, 1.5 Ky 1 minus 1/3 of Ky divided by K load square and bracket closed, right? So you see that's a relatively long formula, but that's a very common formula, like in industry, people use it a lot. So that's the amount of spring back. So this is the spring back we get. So as you can see, this spring back depends on the material, depends on Ky, right? How do we calculate Ky? We just mentioned it here in this page. Ky, we can calculate it from this one, SYEC. So Ky is SY divided by EC, all right? What is C? C is half of the thickness, T divided by 2. All right, now let's stop here and see if you guys have any question. If not, then I'll try to solve one example. So we'll see how we can use this formula in one example. Is there any?
Yeah, I just have a quick question. So, so if we're like designing, we're designing like a part or whatever that has like a bent sheet metal plate. Is this something that we'll have to take into account, or is this something that the machinists would take into account once you like provide a drawing?
All right, that's a very good question. I like it, Craig. Thank you. So Craig is asking, when we design something, should we consider this R, like this spring back, or no? We say this is what I want, and this is the job of manufacturer to take it into account. All right. So there are two things that we can do, and each of them has a cost. Okay. So one is that we design the die. We design the model that what we want, and this is the task of manufacturer to design, to do the calculation and design a different, basically, die. Like here, I ask him that I wanted this radius to be, let's say, 100 millimeters, right? This is what I want, 100 millimeters. Now it is his job, and instead of 100 millimeters radius for this die, he goes and designs something for radius of 80 millimeters, smaller radius, right? A smaller radius bigger curvature. Remember, these two are different, and don't confuse them. So this is 1 over R final. So I asked him that I want a radius of 100 millimeters. He designed the die based on, let's say, just for the sake of discussion now, a mold or a die that the radius is 80 millimeters, right? So that's something that he does. But there is another way, which in a moment I'll get to that one, all right? Which again, is very common to use the second one, because if we want to take into account this spring back, everything is going to be messy, especially if there is just a simple bending, that's okay, simple curvature. But if we get a shape of, let's say, imagine the car, which has all these curvature and bending and all those small radius, then they will be in trouble, right? I'll get to that one, Craig, in a moment. Okay. So let's get to that one now. How to minimize a spring back, okay? This is something that Craig asked. So is there a way to get rid of this spring back, or no, always we have to calculate it? At least we know that there are ways to minimize it. How do I do that? So let's say that I have, again, for simplicity, let's say maybe I have a punch that, let's say, has a radius, simple, like that one. And well, I'm getting, I guess, better in drawing digitally. It's not bad. All right. So
You've definitely improved since Mac 260.
I know. So imagine for years, we have been using either blackboard or whiteboard. Now, all of a sudden, we have to, like for some of us, for me, I'm like old school, like to write on, like I'm more like a chalk and blackboards type. Panos remember me from Mac 260. I like to write on paper, use a document camera, but now switching to digital. You know, some teachers, they don't do that. Like they don't like to do that. Like I guess those of you who have vibration with Gary Shire, he insisted to use still his old style of whiteboard. And it's working fine. But yeah, I switched to this one. Now I'm getting better. So if this COVID continues for another year, hopefully not, then you will see my handwriting improves. All right, so let's say we have this sheet of metal and we want to get to this radius, all right? So we know that after we apply the load, we release the load, we are not gonna get to this radius that we want because of spring back. So people have done a lot of things, they trial and error, and they found something. They said, what if we get to the plastic zone before applying the load, all right? So there is a model which is called, again for simplicity, it is called elastic perfect plastic. I don't know why people, they'll like invent all these weird names, but
it's catchy.
Yeah, but what they mean is, yeah, exactly. It's just, this is elastic section, like a section, and then perfectly plastic, just a straight line. Like somebody one day comes up and says, why do we want this curve? Let's simplify things, like to estimate things. And this is again, is sigma stress, and this is the epsilon. And based on this estimation, probably now we realize if we get to this SUT, let's say to the plastic zone, then they did some experiment and they realized that the spring back is not going to be zero, but it's going to be minimized. So in practice, then what people do is before like doing the actual deformation or forming, they apply load. So let me show it here. like a tension, basically. Yeah, tension T. And this tension get the material to the plastic zone, and then you apply these punch and this press to get to the radius that you want. So in summary, let me write it down here. Before forming, if we tension the plate, so that we reach to SUT or plastic zone, the formation, delta K will be minimized. And this is, in fact, what people do in industry, all right? So coming back to correct question, so as a designer, we design what we want. Now, when we want to manufacture it, we know there is a spring back. Either we can go back and calculate the spring back, because sometimes we have to do that because it's difficult to apply this tension. Of course, it's easy for like a rectangular, maybe plate to apply this tension. If not possible, we have to return back and calculate that delta K for designing the die, right? By designing the die, I mean, you need to know the radius of these things that you want, like the press and the die. You need to do all these calculation, of course, based on the thickness of the things that you want. But it's very common to apply this tension. And of course, when they apply this tension, when you apply the press, there is a lot of friction and heat involved. So there is a lot of oil to reduce the friction and reduce the damage to the plate, okay? So then that's the key. We apply a tension, getting the material to the plastic deformation or plastic zone. And how do we know how much T? Depends, of course, again, to the material and its geometry. We can calculate T, the tension. Let's solve a quick example together.
Can I just ask a question?
Go ahead, Puri.
The tension, does that end up stretching the plate excessively, or is the tension released slightly as it's bent?
So the way that they do it, so Puri asked a good question. We apply the tension. So so in practice, when we apply the tension, do we release it, then we press it, or no, they are simultaneous? This is what he's asking, if I'm getting your question right. No, we keep the tension there, then we apply the press, and simultaneously we release both of these two.
Okay, yeah, that's what I was thinking.
All right, good.
Thanks.
So, no problem. So let's...
So Ahmad, sorry, I got a question.
Go ahead, Panas.
Do we release the tension as the material is deforming or after it's deformed?
No, that's what I said. We release the load and the press simultaneously after the press come down and we did the deformation. Then we release the load. So let's solve one quick example together. It says like this door for a passenger car. It has all these complex features in interior side of it. Of course, you cannot see it inside your car if you have a car, because you have this interior cover basically, but it has all these complex shape and features basically. And so in this example, we are testing two different material. One is aluminum, another one is steel, and we have their properties here. And so what we want to answer is next page, is that we have basically the plate that we use is 2.4 millimeters, all right? First of all, we want to calculate the minimum radius that we can get. That part is easy. We know the minimum possible radius. We just learned the formula for that. Our minimum is E thickness 2 SUT, all right? So that's the first step. And now it says that we want to calculate the spring back for, let's say, one of the radius, which is 21.5 centimeter, and that's the radius of curvature, all right? And we want to calculate the spring back. So again, that one is easy. We know that, or we want to calculate the final curvature, all right? So we know that our final is equal to 1 over K final somebody, I guess, is on mute. K final is equal to the K load that we want to have minus delta K, which delta K is a spring back. And K load is 1 over 250 millimeters, right? That's the radius of curvature of the die that we have. So this is all the information that I have. Now I need to calculate delta K. And delta K has a formula, 1.5 KY, 1 minus 1 over 3 KY divided by KL square. So I need to know KY, and for KY we just found a nice formula, which was SY EC or 2SY ET, all right? And we have all the information that we want, like we know SY, and yeah, and the rest of things that we have all the information. And we know SUT. Don't forget like this one is SUT for our minimum, but for KY we use SY, the yielding strength. All right. I let you guys to use your calculators, and the rest is easy, and find out the values of the final curvature you get for this. Okay.